All right, today we're going to be talking about different types of forces. There are three major types of forces that we're going to be talking about. And an important thing to know is that a force is not a bond. Okay, a force is not a bond. We're talking about the attractions between molecules. So we're going to talk about intermolecular, so between molecules, intermolecular forces. Okay, and basically what that is, it's an attraction between molecules, and it is going to help determine whether we're a solid, a liquid, or a gas at room temperature. So depending on the strength of those forces, if they're strong forces, then they're going to be molecules that are nice and close together, right? Vibrating nice and close together, and those are going to be your solids. If the forces are a little bit less, you might be a liquid, and if they're even less, you're going to be a gas at room temperature. Okay, gases have the least, intermolecular forces. They're really moving around. Okay. It's also strong attractive forces will affect the physical properties. So especially boiling point and melting point, huge. That change between solid to liquid, liquid to gas. Okay, those will all happen, and those will be affected by the intermolecular forces of the molecule in addition to the size of the molecule. Okay, so those are two things that are going to affect those physical properties. All right, so let's talk about our three types of intermolecular forces. They are London dispersion forces, dipole-dipole forces, and hydrogen bonding forces. So remember, it's not a bond, it's a force. Okay, so the three things that I want you to know these three vocab words, and you should know that London dispersion forces and dipole-dipole forces, the two of them together are sometimes called van der Waals forces, and Wall is spelled with two A. Okay, van der Waals forces, because he did lots of work with these two. Okay, so they are attractive forces, and we're going to talk about between what as we go on. So London dispersion, dipole-dipole, and hydrogen bonding are all different types of forces, intermolecular forces. All right, so our London dispersion forces are going to be that basic attraction. Every single atom has London dispersion forces, every single one. Okay, basically it's the idea that you are always going to have a little bit of electronegativity, unless you're a noble gas. You're going to attract another atom's electrons. Okay, so for a noble gas, they might be the one that's having their electron attracted, right? So you're going to have your center of your nucleus that's positively charged, and it's going to attract another atom's nucleus. There's going to be just a small attraction. It's not going to make them right next to each other, but it's going to be a small limited attraction. So if you guys see this picture, if I am looking at this nucleus right here, this is going to attract to this electron. Okay, that little attraction there is going to be called the London dispersion forces. Okay, at the same time, these electrons here, right here, are pushing away from each other. Okay, so that's why the atoms don't get nice and close, is that you have to remember that all around the nucleus, there's those electron clouds that are pushing those atoms away from each other. Repel, okay? Electrons repel each other. Okay, so as your electrons are moving around, they're typically repelling, okay? And then in a flash of a little instant, you're going to have this nucleus attract to this electron, and then it's going to be gone. Okay, so it's a momentary exposure, okay, that allows this attraction of the nucleus with the other electron. All right, let's try that out. Okay, next up we've got dipole-dipole forces. So this occurs only when you have polar bonding happening. So you need to say, are there polar bonds, yes or no? And if there are polar bonds, then there's going to be some dipole-dipole forces. So it only occurs with polar bonds. It's also going to be a stronger attraction than London dispersion. So London dispersion is the weakest force. Dipole-dipole is a little bit stronger. And basically what it says is that you're going to have the partial positive, that's sigma plus, remember, sigma plus, and the partial negative, sigma minus. Negative ends of a polar molecule attract to the opposite ends of another, okay? So here we've got this partial positive. So suppose this was Cl and this was H, right? This would be your partial positive, the H. Same thing, this is a Cl and this is an H. Okay, so this hydrogen, this partial positive where there's less electrons, is going to attract to this area here where there's more electrons, and it's going to pull them a little closer together. You'll also notice they're arranged similarly. Same thing as when I draw molecules, I tend to draw them all facing the same direction because they'll order themselves, okay? Because the partial positives will be attracted to partial negatives of another dipole bond, all right? So that's your dipole-dipole forces. Hydrogen bonding is the strongest attraction, okay? It's the strongest attraction, and basically what it is it's a pretty extreme version of dipole-dipole bonding, and it only works with certain elements, okay? It works when hydrogen is bonded to either N, O, or F, okay? So sometimes if you try and say it with an accent, you can say hydrogen bonding is fun, right? It's fun. Okay, so that's a way that you can remember it. All right, so we've got hydrogen bonding to N, O, or F. So that's an H to N bond, an H to O bond, or an H to F bond. Okay, those are your three choices. If it's one of those, then it's going to be hydrogen bonding. Okay, again, not a bond, it's a force. So hydrogen bonding force. Okay, it's an intermolecular force between molecules. Okay, so you can see the way that these water molecules are arranged. We've got our oxygen, which is the red, and then we've got our hydrogens here. And you can see that this hydrogen here is electropositive. It's got a sigma plus, and it attracts towards this sigma minus, okay, that the oxygen has. So this lack of electrons, so the attraction is going to attract to where there are a lot of electrons in the oxygen. All right, so that little attraction there, you'll see it's noted by little dots to show it's not a bond, it's just a force. Okay, hydrogen bonding is the strongest intermolecular force. And the reason this happens is, think about what hydrogen looks like. So we've got our center nucleus, okay, and then we've just got one electron. Okay, so this electron is going to be moving around, and it doesn't have any other layers of electron orbitals to shield it, okay, to kind of block it from the electrons of another nucleus, okay? So you're going to have a lot of bond strength, okay, coming from your hydrogen, right? Because there's nothing to shield your nucleus from the other electrons. And that electron, and remember, this electron is moving around, so it's not always in one spot, it's moving. Okay, so all the other spots are going to be pulling and attracting closer to other electrons. Oh, sorry, not to other electrons, to other atoms. This nucleus is going to attract to the electrons of another atom. Okay, let's see an example where hydrogen bonding is into play. Okay, the most common place that we all have heard about, especially coming out of biology last year, is going to be in DNA. Okay, so DNA, we remember, has those base pairs, AT, GC, right? Sometimes U gets thrown in there. Okay, basically what happens is if you look at this double helix, it's hard to figure out, but in the center, they're not actually bonding and they're not touching. Okay, but what they are is they kind of zip up like this because it's hydrogen bonding that creates this pull together. So this is hydrogen bonding that keeps that double helix zipped, almost like a zipper. Okay, so it says strong, strong force. So if you can see, this is a dotted line. So this is a G base pair, a guanine, and this is a cytosine base pair. Okay, and this hydrogen is being attracted to this oxygen. This hydrogen to this nitrogen, this hydrogen to this oxygen. So that helps keep those base pairs close together because it's strong attractions between hydrogen and either hydrogen and either N, O, or F. N, O, or F. O and N are very popular in organic compounds. They're in our body a lot, so we do see a lot of this, especially in DNA. So that's the next example for hydrogen bonding. All right? Awesome. Nice work.